Great, thanks, Ernest, very much. So this is a picture of the dock, one of the docks for our sailing club at UW-Madison. If you don't know our campus, it's right on this beautiful lake here. It's about 12 kilometers across. And I sail these little boats here, these little one-person boats, but we also have much bigger boats and so on. But anyway, it's a No. Mine's one of these little, humble little ones here. But it's one of the great attractions of our campus is that you can learn to sail there, and we have a fantastic club. This picture was taken on July 3rd, 2021, which was a particularly spectacular sunset. So I'd like to talk about this paper. Like many other people at this meeting, I'm talking about min-max, and it's a subject that I'm not nearly as familiar with as quite a few people here are really experts in this area. And this is work with two colleagues. So one is my postdoc, Ahmed, who's very well known to some of you. And you'll notice that there's a lot of diversity here in the author list, particularly in terms of age, because I'm 63, and I think Ahmed's in his early 30s, and Dongwan's about 12. So anyway, so I'll talk a little bit about our... sorry, what was that?
Yeah, very good.
Let's see. So I'll talk a bit, first of all, define the problems that we're dealing with. And there's a lot of emphasis here on non-monotonicity. So I'll talk about the particular non-monotonicity conditions we use. And I also need to make a lot of definitions. A lot of them are things that are familiar to you, but there are some more recent definitions that I'll probably need to go over. Then I'll talk about how we formulate these problems as fixed point problems for the purpose of then designing these two loop algorithms. These are algorithms with an outer loop and an inner loop. And all the ingredients are fairly standard here, but they're kind of assembled in possibly somewhat novel ways. So the outer loop is either a Halpern or KM. I'll say what KM means in a moment. Inexact version of those two methods, and the inner loop is just Paul Seng's forward-backward-forward method. For monotone inclusions. And then I'll just, if I get time at the end, I'll talk about some open questions. So here's the min-max problem. Everything's fairly smooth here. I'm not doing anything particularly non-smooth unless there are constraint sets there that you can hide things in. They're both convex, but the F I'm going to assume is not necessarily convex. And there was a talk yesterday, I'm sorry I forget who it was, but they put up exactly the same list of three possible applications of non-smooth as that I have here, and I didn't copy it, so we came up with that list independently. And another target problem is this non-monotone inclusion. So here F is a map from RD to RD, and again it's L Lipschitz, but again possibly non-monotone. G is a set-valued mapping that's maximal monotone, so again that could be a set indicator. And I'm going to sort of focus a lot on two special cases. The first one allows non-monotonicity, but only to a restricted degree. And specifically, we allow the F plus G, the combined operator, to be co-hypermonotone. And what that exactly means is given here in the next line. There's some positive constant or non-negative constant rho, such that if you take X and U and Y, V in the graph of this operator, the inner product satisfies that condition there. It might be a little bit clearer if I go to the next slide and just get rid of the G and just think of this as a problem of solving f of x equals 0, where f is a square operator. If you get rid of the G, then this statement simplifies quite a bit, and it's just a co-hypermonotonicity condition, where again you've got this rho. And there are these works that defined this condition before. So the other thing I'm interested in, going back to the more general case in the previous slide, is the stochastic case where we only have oracle access to the F. So we're not able to evaluate F exactly, but we can evaluate an unbiased oracle, which is also a function of a random variable, and such that the expectation of the random variable equals the exact value. So I'm going to talk a lot about those two cases. All right, and of course, we all know from Terry's book in 1970 that you can express the min-max as a non-monotone inclusion by defining the G to be the indicator function for the two sets, and by defining the F to be, the partial gradients of the objective, min-max objective F. So in the stochastic setting, when I'm talking about oracles, I mentioned the oracle on the previous slide. For this problem, we could have oracles that give you unbiased gradients, according to this definition. And most theory for stochastic gradient that we've also heard a lot about at this meeting assumes access to unbiased oracles like that. And I'm going to assume that the U and V are simple enough that you can project onto them exactly. Okay, so here come some definitions, and as I said, most of these are fairly familiar. The first one I've already told you about. The second one is kind of a specialization of the first one, to the case where we don't allow the y to be general, but we fix y to be the solution of the problem, the point that we're particularly interested in. And if y is a solution, that means 0 is in the graph of y. And so V is in the graph of y, so the V disappears here from this expression, and y is just replaced by x star. So that's a weaker condition, and it goes by several names, but we call it rho star cohypomonotonicity. There's a lot of tongue twister names here. Strongly monotone, that's a condition that you're all familiar with, I'd say. And then co-coercive, if I get rid of the G and I just deal with F, co-coercivity looks like this condition here. The difference with cohypomonotonicity is that the coefficient here is positive rather than negative, as it is up there. Okay, the resolvent, again, this is a generalization of the Prox operator, and again, a very well understood concept by now. So given a set-valued operator H, we define the resolvent like this. If H is maximally monotone or cohypomonotone with the tau sufficiently small, then you can be sure that this is single valued, okay? And in fact, we sort of ensure that's the case by putting a scaling factor in front of the thing that we take the resolvent of. We put an eta in front of it to make sure that we do have a single valued resolvent, and that I'm just kind of assuming throughout. So if the F comes from the min-max problem, so if the F consists of the partial gradients like it does here, then the resolvent can be stated as an argmin-max problem like this. So you plug in the U and V, and you solve this argmin-max problem to get you the resolvent. If you write down optimality conditions for that, you can match it up with conditions there. Okay, now some flavors of non-expansiveness, and this is the last heavy-duty definition slide I have. So obviously, if we've just got a single-valued operator, it's L Lipschitz if it satisfies that first condition. If the L is 1, then it's non-expansive. We make a big deal of this firmly non-expansive condition. So firmly non-expansive, as its name suggests, is a little bit stronger than non-expansive in that you have to be less than that by at least that amount. Now, is a much easier definition, and it's just to say that T is firmly non-expansive if the average of I and N, if T can be expressed as the average of I and N, where N is non-expansive. Okay, so it's a little bit stronger than just non-expansive. Now, here's a fairly new one, alpha conically non-expansive, and that's mentioned in Heinz's book. I'm not sure if his definition's original with him or whether it goes back further. But that's this definition. It says an operator is alpha conically non-expansive if there's another non-expansive operator N such that T can be expressed like this for some alpha positive. Alpha doesn't have to be between 0 and 1, okay? Any positive number. So this could actually be negative, the coefficient of I. And you can write that equivalently. If you just solve this for N, you can write this equivalently as that 1 minus 1 over alpha times identity plus 1 over alpha times T is non-expansive, and that's what you need for T to be alpha conically non-expansive. Now there are all these relationships. So if T is alpha conically non-expansive, then 1 minus T is 1 over 2 alpha co-coercive, and if K is cohypomonotone with some rho between 0 and 1, then this resolvent and blah blah blah. So you can prove lots of sort of technical relationships between these different concepts. But one we use a lot is that if the rho is less than 1/2, if K satisfies this cohypomonotonicity condition with rho less than 1/2, then JK, the resolvent of K, is non-expansive. Turns out we use that. So here's an important consequence of all those definitions. So going back to our original assumption about the inclusion, if F plus G is rho cohypomonotone, then you can use some of those technical results from the previous slide to say that the resolvent of eta times f plus g is 1 over 2 alpha conically non-expansive, or we define alpha like this, 1 minus eta over rho. And that means that this resolvent is single valued, provided that the rho is less than eta, which means that the alpha is between 0 and 1, okay? And that means that this guy is non-expansive, and that just comes from this, applying this property here, or one of those properties, I forget which. Anyway, that's non-expansive. And then using the definition of this operator T, if T prime is non-expansive, then this operator is firmly non-expansive, okay? And this operator, if you plug in the definition of T prime here, you just get this object here. So you take the f plus g that defines the inclusion problem, you scale it with eta, where eta is greater than the rho, which is the correspond expression. You define the alpha like this, and you end up with a firmly non-expansive operator. So why do we care so much about that operator? Well, I'll probably skip forward a little bit here. The reason we care about it is that fixed points of this operator, T, are actually fixed points, are actually solutions of the inclusion, okay? So we'll see that in a slide or two. So we work with this operator a lot, this actual operator T. Okay, so our goal is to rewrite the inclusion as a fixed point problem. So if I've got an operator T that defines a fixed point problem, I'm seeking a point x star such that x star equals Tx star. Here are some classical methods or iterative methods for converging to a solution of that problem. The Picard iteration is very old. It's just, you just keep pounding it with T. The KM or Krasnoselskii, excuse me about that, Mann iteration is a little bit more complicated. It takes a convex combination of x and tx to get the next iteration. Then the Halpern iteration looks like this. So you sort of have this anchor point, which is the initial point x naught, and you take a convex combination of x naught and t times xk, but the coefficient of this combination shrinks towards 0 as k grows. And then you can prove that that converges as well. So we're going to use certainly the last two, and you could argue we also use the first one in some of these algorithms. How do we measure progress towards a solution? Well, the natural thing to do is just to take the difference between the left and right-hand sides, since this is a fixed point problem. So we keep track of this distance, and we hope that that shrinks to 0 at a certain rate. So we get complexity results by saying how big k has to be to reduce this quantity below, say, epsilon squared. Okay, so here's our strategy for solving the inclusion problem. First of all, we restate as a fixed point problem, and we use two different restatements. The first one is kind of the more obvious one. Just if x star is equal to its own resolvent, which is, here's just the definition of the resolvent, you can show by just solving for x star that x star is 0 belongs to the f of x star plus g of x star. But this operator here, this is exactly that T I went to all the pains to derive a couple of slides ago. This is a combination of the resolvent and the identity. And that gives us another fixed point formulation of this problem, okay? And we use both of those in two different algorithms. So the outer loop, as I mentioned earlier, the outer loop is either the inexact Halpern operation or the inexact KM. And basically the Halpern we apply to this operator here, so you'll recognize that guy there. And the KM we apply to the resolvent, so you'll recognize the resolvent there. You just plug into the definition on the previous slide. Now, it's very important that we want to be able to use an inexact version of the resolvent, because computing that exactly can be quite onerous. So that's where the inner loop comes in, where we have another loop which calculates an inexact version of the resolvent. We call that J tilde. Okay, and we choose the eta to make sure that that problem, that subproblem, is strongly convex, strongly concave. And therefore, there are nice methods like extra gradient that solve that with linear convergence. And in fact, they have optimal first order complexity. So this is our basic approach. Fixed point formulation, classical iteration for fixed point iteration for the outer loop with inexactness, and then an optimal first order algorithm for the inner loop. Yeah. Yeah, that's a good point. I'll get to that in a moment. Yeah, excellent point. I've got a couple of slides about that. So here are the details of the inner loop. So as I said, this is a tribute to our friend Paul, this forward-backward-forward algorithm, and I won't go into the details of this, but basically we use it as a subroutine where we plug in two operators, A and B. In fact, it's called Bn for sort of complicated reasons. The B is the one we can apply explicitly, and the A is something like the set inclusion. So it's something where we can evaluate the resolvent of tau times A explicitly. That's like a projection onto a simple set or something like that. So this series of iterations, it turns out, if you run it long enough, it'll give you the solution to a set valued inclusion involving A and B. So I won't say too much more about that guy, but this is the outer loop. I guess I'll get back to it when we start talking about the stochastic case. Because in the stochastic case, we only have oracle access to the F, and the A or the B operator is actually the F. It's made up of eta times F, and so we may not be able to get exact access to B, but only oracle access. So we have a stochastic version of this algorithm as well. I'll say a little bit more about. Okay, so here's the outer loop. So I'm going to start with the Halpern variant, and the thing that I've got highlighted in the red here is exactly that T operation that I defined earlier, the combination of the resolvent and the identity. And so this is just classical Halpern with that operation, and here's what we call FBF. So you can see that the A is just tau times eta times G. The B is identity plus eta times F. So that's this operation here. And then this is the Lipschitz constant for the B. So remember, F has Lipschitz constant L, so the Lipschitz constant for identity plus eta times F is just 1 plus eta times L. Now, the critical thing here is deciding how accurately we have to evaluate the resolvent, the J tilde. And so we need to actually satisfy this condition here, that the difference between the true and the calculated, inexact version of J is bounded by this epsilon k. And we have to, of course, be very careful about how we choose the epsilon k. And what we do here is we choose the number of iterations of the inner loop, which is this nk. This is how many times we loop through the FBF algorithm. We choose it so that when we exit from FBF, that inexactness condition is satisfied for this value of epsilon k. Okay? And if we just look at this value here, the numerator would be 0 if xk actually was a fixed point of the resolvent. Okay? So it's a relative error in some sense. You know, the left-hand side over here is the difference between the two resolvents, and the right-hand side, it looks like it's the square of the actual result, or the actual resolvent. But probably the important thing here is that the denominator has a square root of k in it. The log term, we always just kind of more or less ignore those. So there's a square root of k. So you can see that generally this thing is going to be decreasing, because we'd expect the numerator to be shrinking, and we expect the k to be growing, and it is growing. So all over the epsilon k goes to 0. The question is, how fast do we need it to go to 0 in order to still get convergence of this outer loop? Okay? By the way, this is how you would implement the FBF. I probably shouldn't dwell on this, but the inner loop, I've written it as a bunch of inclusions, but if you go back to considering the specific min-max problem with the F and the U and the V, this is how you actually implement the inner loop. So you can see things that look like gradient descent and ascent steps. You can see projection operators. You can see, you know, averaging stuff going on. So I won't dwell on that, but clearly it's implementable for the min-max problem. Okay, so what do we get when we're talking about the outer loop? So that, again, classical theory here says if we look at the outer loop iterations, the xk's, we want this thing to go to 0 to solve the fixed point problem. And in fact, it is going to 0 like 1 over k. So in order to reduce this guy below some given tolerance epsilon, we need k equals this many order epsilon inverse iterations of the outer loop. Okay? Now, what about the number of inner loop operations? So the nk, if we go look at the formula for the nk, that's the number of times we have to iterate FBF. Notice that the k only enters here as a log. So we've got a constant here. The eta has to be less than 1 over L in order to make the denominator positive. But we've just got a constant, except that it depends logarithmically on k. So in other words, nk is order 1 to within log terms. So the overall complexity, the number of times you need to evaluate f and the resolvent of g is basically order of epsilon minus 1. So we've actually got a little bit of a contribution here beyond, there's been quite a lot of literature on this cohypomonotone problem, but interestingly, all of it, including all the papers we cite here, as far as we can tell, require the rho to be less than 1 over 2L. Remember, L is a Lipschitz constant for the F. So they've got this bound on rho. You can't be more than that much non-convex. We're able to extend that to 1 over L. So we're able to tolerate a little bit more non-convexity. Okay, so that's one thing that we do. So let me jump ahead and look at that a little bit more, and this goes to answering John's question. So first of all, why do most of these previous works get stuck at 1 over 2L? Well, they use the following two facts, or the following two needs. The first one is that you need this resolvent to be non-expansive. And in order to do that, the cohypomonotonicity parameter has to be less than or equal to 1/2 of the eta, the scaling that we apply here. You sort of think of it as a step length. So you need that inequality satisfied. And the second thing you need is that in order to run that inner loop, you need that operator, you need this problem, you need that subproblem to be strongly monotone. In order for that to be true, you need the eta to be less than 1 over L, because L is a Lipschitz constant for the F. So you need these two conditions both satisfied, and if you put those two together, you can see that the rho needs to be less than 1 over 2L. So that's the logic that most people use to sort of say that was as big as we could allow rho to get. But our secret sauce here is to use this operator T as the thing that we do in the fixed point formulation rather than the original resolvent. And using that operator, we still need the non-expansivity property, so we still need rho to be less than eta over 2, but we can now let the eta go up to 1 over L. Okay, where did I screw this up? So the eta, oh, that's right. No, we can replace this. We don't need the resolvent to be non-expansive. We need T to be non-expansive. And that's a looser condition. Instead of rho being less than eta over 2, we can now let just rho be less than eta. Okay? We still need this property, that the eta has to be less than 1 over L. But if we plug this and this together, we get this larger allowable range of the rho. So we can go to a bigger value of rho. Okay, let me jump back to this guy. The other thing we try to do is to tighten up the analysis of the inexact Halpern. And the comparison, the paper we were trying to beat here was our colleague Jelena Dyker-Nicholas had a paper from 2020 on Halpern, but she was applying it to the inexact resolvent rather than the operator T that we use. And she needed the inexactness condition. She, by the way, only did it for the monotone case. And in the monotone case, the T just reduces to the resolvent. So the two methods kind of, the T loses its specialness in the monotone case. So the rho is equal to 0 in that case. So, but you can extend her analysis to the sort of, to sort of our setting. And you need the epsilon k. These are the parameters that govern how accurate the tolerance has to be. You need the epsilon k's to satisfy this inequality here, which translates into epsilon k being approximately 1 over k cubed within a log factor. Now, to get that, she uses analysis based on non-expansiveness of this operator. Now, we have this firm non-expansiveness, and that gets us more. We actually get a relaxed condition for the epsilon k. So we only needed to satisfy 1 over k to the 3 over 2. So we can allow more slop in the calculation of the inexact resolvent. Now, if you've got a linearly convergent inner loop, this difference hardly matters, right? Because this just comes in as a log. Yeah, sure, thanks, Ernest. This just comes in as a log. But the reason that it's potentially interesting is that I'm now going to look at solving that inner loop problem with a stochastic oracle. And now you only get arithmetic convergence rather than linear convergence. And now there's a fairly dramatic difference between these two tolerances. You see the complexities ending up being quite different. Okay, so here's the inner loop for the stochastic case. So again, these are just the two problems we have to solve for the resolvent. So in the stochastic case, this is in fact, this is a problem we're solving in the inner loop. We have to do this inexact resolvent calculation here. And so if you run a stochastic version of FBF, which I don't have the space or the time to describe, but basically every time you evaluate that B operator, you replace it with an unbiased oracle, the inner loop converges now arithmetically. So after n iterations of the inner loop, you get order 1 over n accuracy. So if you're trying to achieve this level of accuracy for the purposes of the outer loop, the amount of, the n has to be now epsilon k to the minus 2, okay? So if you look at these two algorithms, epsilon k here is 1 over k cubed. If you take that to the minus 2, you're going to have to do k to the 6th inner iterations at iteration k of the outer loop, all right? Here it's only k cubed. So now you see a pretty dramatic difference if you're doing a stochastic inner loop. And so what you end up with is that if you apply Yellen-Dike-Nicholas's algorithm from 2020, the overall complexity, if you take the 1 over epsilon from the outer loop, the k to the 6 over the inner loop, you're going to need this many total operations, inner loop operations, to get epsilon accurate solution to the fixed point problem, epsilon to the minus 7. Whereas we only end up with epsilon to the minus 4 because we've got a k cubed inner loop. And so we claim this is novel even in the non-monotone case. Previously, something like this had been obtained, but they needed this uniform Lipschitz condition. This is a very recent paper, and ours is a last iterate result. And as best we can tell, if you apply the analysis of this paper, you get a much worse complexity. Okay, so I'm sort of out of time, but if I had more time, and I'm happy to share the slides, I would go on to describe what we do in the rho star monotonicity case. And basically the theme is that we don't use that special operator T anymore in the fixed point problem, we just use the resolvent. But here we've got the Km iteration. It's got slightly worse complexity. Instead of 1 over k, it's 1 over square root of k. So we end up with a worse outer loop complexity. It's epsilon to the minus 2. For the inner loop, again, we can use, in the deterministic case, we can use, I'm skipping a whole lot of slides here. We can go ahead and use, we can just use FBF again. In the stochastic case, things get really interesting because we have to come up with unbiased estimates. Sorry, I'm flying all over the place here. We have to have unbiased estimates of this resolvent. And having an unbiased estimate of F is not enough to give you unbiased estimates of this resolvent. So we have to resort to all of these tricks, basically involving this multi-level Monte Carlo strategy. That's something that Niao, I don't think Niao's here, but she has a recent paper where she used that, right? This MLMC. And it's a way of getting vastly reducing the bias in your estimate of the resolvent of J. And we also do batching and averaging and so on to get that down to a reasonable level. And so that becomes significantly non-trivial. So that part I'm skipping over. But just jumping to the end here, we end up with an epsilon to the minus 4 convergence. We still, for the unconstrained case, there's a recent paper. This is not Tom, by the way. You'd think it was Tom because Tom works on everything, but this is a different low. And they get an epsilon to the minus 2 in the unconstrained case. And we want to understand why we can't match that. We're also interested in seeing if there's a single loop algorithm that works, and so on. So that's it. And notice that there's an awful lot of people here and their colleagues who've contributed to this area. And so thank you very much. And I'm sorry I went over.